In the first part of this video lecture, we have discussed what it means for a random variable to be absolutely continuous. That's exactly when its distribution has a Radon-Nikodym derivative with respect to the Lebesgue measure. Then we have seen two of the main examples of random variables that have a density. One is the normal, and the other is the uniform on 0, 1. And then we saw that changing the value of a density on a set of measure 0 will not affect the property of it being a density. And now we're ready to state a proposition that will reconcile our notion of expectation first with the notion of expectation we had last year. And most important, now we can actually compute expectations. So we tossed on the bin an object that was very convenient to compute for one that was very robust in terms of its mathematical properties. And now we reconcile them both, so we have the best of both worlds. We have an object, the expectation, which was defined properly, which has all those convergence theorems, linearity, monotonicity, all those properties that we love. But now we can also say we can actually compute it, and we can compute it like this. So what this proposition is saying that if we have a function, well, this function g of x, it can be, for instance, just the positive part of x, if you want. So we can compute the expectation of x plus using this formula, and then after that we can compute the expectation of x minus and subtract. So as you see, we are opting for this non-negative measure theory, where if some function is not non-negative, you can just split it into two. So this is saying the expectation of a random variable x in particular is equal to this integral. This we're very familiar with, and let's say this is the integral on r plus. Okay, and in general, this function can be here anything, which means that if we want to compute the expectation of x squared, the expectation of x squared, there's something tricky here, and this is why this is called the law of the unconscious statistician. So we were computing the expectation of x squared. Well, in theory, we would need to understand what is the distribution of x squared, then compute the density of x squared and integrate that. This would be the proper way of computing the expectation of x squared. It's just we're calling x squared, we're calling it z, and here we find the distribution, cumulative distribution function of z, then we find the density of z, then we integrate z against its density. This would be the proper way if we think about it for a while, but we can also do it differently. We can see, well, whatever function it is, here's the function square, I can also compute it like this, and it gives the correct result. So this is the law of the unconscious statistician, and it's called like this because most people use it without even realizing it's not really the proper definition of expectation to just put whatever function we want here and put it here. In fact, it is a proposition, which we prove. Now the proof of the proposition, it has two steps. One step is first to consider the push forward of a measure. Wow, the push forward. You remember this from the previous unit. Okay. How the push forward? Well, we have omega, that's an abstract space, and then we have a function x. I don't like to call it function. It is a random variable, but mathematically it is a function. Then it takes us to this space here, the real line. And now we're taking g and composing g with x to get another random variable, taking values here on the real line. And we have seen already that in order to compute the integral of this composed function on omega, we can also instead So with respect to some measure, yeah, of course, there's some measure here, p. So we want to integrate this composed function with respect to this measure p. What we can do is instead, we can push the measure p forward. Then we get here x star p. That's the push forward, which we like to call px. I think green over green is not a good idea. So this is we push forward the measure, and now we integrate only the last bit of the function against this push forward of the measure on this space rather than on this space, which means we can erase all details of this abstract space here where all our randomness is taking place, and just consider this space here, the real line. That's the space where x takes its values. We push the measure forward to this space, and now we just have this function g to think about. Well, all that is just to say this integral can be computed this way. Okay, I'm replacing my abstract probability function on sample space by the distribution of x. And I'm integrating g only instead of the composition of g and x. Okay, so this is a compact notation, it's g with the push forward measure. And now we're going to use, let us go back here. From the previous video lecture, we're going to use here the chain rule. So the fact that if a measure is has a density with respect to another measure, then we can replace it by the other measure and multiply by the density. And this is exactly what we are doing here. So we are taking, we know that the distribution of x has a density with respect to the Lebesgue measure, so we can integrate with respect to the Lebesgue measure as long as we multiply here by that density. Okay? And then this is what it becomes. The density is fx, that's by definition of x, fx, it is the density. So this equality holds, and this is equal to this. So this proves the proposition. What was the proposition? The proposition was that the expectation of g of x can be computed this way. Here's an example of how we use that proposition, and we are using here the function g of x equals x plus. Okay, and so we take a function x that has an exponential distribution with a certain parameter lambda. We're going to see that the expectation of that random variable is 1 over lambda. And how do we do that? Well, we know what the density of px is. We have seen that already. This is the density of the distribution of x with respect to Lebesgue measure. And how can we compute the expectation of x? Well, the function x, we just plug it here. We already know expectation of x minus is 0 because x minus is the probability that x is negative is 0. So we put x here, and this is the integral on r, but this is actually an integral on r plus because everything is 0 outside r plus. And we can compute this integral. We can compute, so this becomes an integral on this space of x lambda e to the minus lambda x. You know what to do. You use monotone convergence theorem. Since this is non-negative, the integrand is non-negative, we can instead integrate this on 0n. Let me change colors. We can integrate this on 0n, and this will increase as we increase n because the function inside here is non-negative, and then we take the limit in n, and well, we know how to compute this integral. We integrate by parts, and we know what the result will be in the end. The result will be 1 over lambda. This concludes this video lecture.